Let's talk about image editing. So this is something I've been wanting to talk about for a while, and this video is probably going to be longer than most. I'm going to be covering multiple papers, which is different than what I usually do, but it's just because the papers I don't think they're big enough to cover by themselves, but I think they go together really, really well. And it's kind of this new approach I've been seeing towards image editing. So I'm going to be covering kind of what the current state of image editing is with like diffusion models. Of course, it's going to be a diffusion model. I'm going to be assuming knowledge of diffusion models. So if you don't know kind of how diffusion models work, go ahead and check out another video on diffusion models. I've made one on diffusion models, a few. There are other videos that are probably better. Just go check out one and come back here, I suppose. So I'm going to be covering kind of inversion techniques in this video. Mainly because I think that they may be the next thing for image editing. But anyways, let's get started. So going to be covering kind of the current state, and then some inversion techniques, and then kind of how to use those. So first off, why are current image editing techniques bad? So what are the current image editing techniques? Well, there's quite a number, but I'm kind of going to classify them into a few categories. So we will say that the first one is going to be like image to image. And the second technique is going to be, say, conditional. And then the third one I'm going to call inversion. Now, image to image kind of has the least amount of control, but the most variance. Kind of what I'm arguing. This has the least control and the most variance, while inversion kind of has the most control because it has the least amount of variance. And I'll get to why I'm saying that later. So let's just go through kind of these approaches one by one. So image to image. We all know and love image to image. If you've used some stable diffusion platform, you've probably used image to image. Basically, there's kind of two main things you do with image to image. So you basically have an image you've already generated. And the goal basically of all these techniques is we have an image, we want to edit it in some way. So maybe we have a picture of a cat, and I don't know, I have this as like some normal looking cat. Maybe this is like a picture of a happy cat. I don't know. And maybe I want to change it to like angry cat. So I don't know, maybe I want it to look like that. But how do you do this? I'm not creative enough to go and edit this picture myself, so I'm going to be using some method to do that. So what you usually will probably do is use some diffusion model to do this. And this diffusion model will use this image to image editing. So you're going to send this through the diffusion model, it'll do some image to image editing, and it'll give you something back. Now, if you've used image to image, basically what you do is you're going to take this image here. And we all know and love the diffusion process. Basically, the diffusion process starts out with an image. This will be x0. And it ends with some noise. We'll call this xt, which is equal to epsilon. So it's an increasing noise through the forward process. So this is the forward process from time x equals 0 to time t. And basically all you do is you just add noise. And then the reverse process is going to generate an image from noise. So basically x at time t is going to be equal to some linear combination of your input signal and your between signal and noise, where we already have this, and this is just used to edit the image, or you can generate an image from pure noise, whatever. So basically some variance, maybe alpha t times x0 plus 1 minus that variance, or something like that, times your epsilon, where epsilon is usually sampled, that's a disgusting tota, from a normal distribution. Now, to edit an image, basically what you usually do is you're like, well, I kind of want this image to be edited a lot, or a little bit, because I just want it to kind of change the emotion. So maybe what you'll do is you'll go halfway into the process and you say, I want this to be noised at, say, 0.6%, so 60%. And what this is saying is I'm going to go forward in the diffusion process 60%, and then I'm just going to have the diffusion model basically edit the image according to this new prompt however much I want. And basically what you do is you take your image, you add noise using the forward process, which is just this, using some number of steps to get 60% noised. So you're going to have 40% signal, 60% noise. Well, kind of. I'll go with that for now, but depending on how your scheduler is, it could be more or less. But 60% into the forward process. And then the diffusion model is going to denoise that. Now, the problem is you make it a cat that looks kind of angry, but it's not going to be your cat. Like, if this is my cat, this is my pet cat, this is obviously a picture of my pet cat. I don't want the output to be some weird looking cat that is angry. Maybe it will give me a picture of angry cat. There we go. Like, this isn't my cat. This isn't the picture I originally took. And this is the problem with image-to-image techniques. You go forward, and you basically invert this forward process by having the diffusion model denoise your noisy version of your image. But the diffusion model doesn't care what your original image was. It's just going to generate whatever is most likely because it was trained in that way. Now, you can add some control nets. You can condition this on, say, or you can add some control nets here saying, I want you to keep this my cat. But that limits editability, and it sometimes doesn't work as well as one might expect. So you can add control nets and stuff like that, but it's usually not as good as one would hope. And this also applies to masking. So if I say, maybe I just mask out the mouth right here, everything else will be the same. It's the same exact idea as here, except you're just editing this part here, while the rest stays the same. And you can train you can train an image editing model or in-painting model as well. But that requires you to, 1, train an in-painting model, and 2, it may also generate something completely different here. Maybe I want to generate a picture of my smile, and it outputs a picture of a stock photo smile, or it usually generates something that isn't desirable. It isn't you. It isn't the original picture. This is the problem with image-to-image. And it's actually the same problem with conditional generation as well. So conditional generation basically is slightly different. I kind of classify them differently because they're slightly different. This kind of takes it one step up, making you have more control over the process, but still not enough to be desirable. Basically, what you can do is you can train, say, a new model or fine-tune a diffusion model to take in some noise, so normal diffusion model, and output something, so whatever that may be. So normal diffusion model, but instead you can condition it on, so instead of just conditioning it on text, say like a picture of my cat, you can also condition it on a picture. And maybe this will be the picture I have up here, so it'll be the picture of my cat. I'm just going to take my cat. There we go. So we can condition it on this, and we can train this new model to basically keep whatever the original subject is the same. This is a diffusion model. And to generate something in the output. But these methods still run into a problem. And the reason they run into a problem is because notice how the input has variance. And if you're feeding variance into a model, you expect there to be variance in the output. So you can't really expect it to give you kind of the same subject and to just edit some small details. If the model has this massive variance that you're conditioning it on. So this is a problem with kind of conditional models. Like, it gives you more control than these models up here, these techniques up here, but it requires training. And since you're giving it a lot of variance, the output's going to have a lot of variance. So it doesn't do as good as one might hope. Now, inversion techniques, basically the idea, it's similar to up here. The idea is not just to find an arbitrary noise at, I'm not going to say 60%, but say 100%. The idea is to find a one-to-one correspondence between your image and your noise. So this is what the inversion idea is. It's not finding an arbitrary noise thing, or an arbitrary noise latent that corresponds to this image. It's finding a one-to-one correspondence between the noise latent and the output, and the input image you give it. Now, if I were to find a one-to-one correspondence and I invert an image such that I get the latent corresponding to that image, then what I can do is I can feed this latent through the diffusion model and do the denoising process to give me my original image. Now this is good because this basically gives you your original image, and since it gives you your original image, you can slightly move in the latent space near this noise to change features, but move slightly such that it doesn't change your original image too much. And I think these techniques are a lot better than the current techniques being used. At least they seem to be more promising, and that's because it gives you a lot more control than these other methods. It allows you to stay close to your original image, or you can go far away from it if you want. It also allows you to do inpainting if you just want to edit, say, the mouth here. And there's a lot of there's a couple approaches I want to show for this. Now, first off, like if you already know DDIM and DDPM really well, just skip this part. I want to derive DDIM and DDPM to give some good intuition for basically what it's doing. Just some intuition I want to give. If you already know this, go ahead and skip it. But basically, I want to derive DDPM and DDIM and talk through kind of what they're doing. I feel like it'll give some good intuition. So basically, let xt, so this is going to be our image at time t, be equal to, so this is just normal DDPM. This will be our noise scheduler at time t, times x0, where this is our signal, plus the square root of 1 minus alpha t epsilon. So this basically gives you an interpolation between your signal and your noise. So we have x0 here, we have our noise here, and we have some trajectory between the two where this corresponds to x at time t. Now, it's not going to be a perfect flat trajectory, because if it was, you can do this in one step, but you need solvers so that you can solve this in multiple steps, because it's a curved trajectory, unfortunately. So let's derive DDIM and DDPM from this. So basically, I just want to do this. So first, I'm going to move this to the other side. So xt minus 1 minus alpha t times epsilon is equal to alpha t x0. And then x0 is equal to xt minus the square root of 1 minus alpha t epsilon over the square root of xt, or alpha t. So basically, my goal here is to show how we can invert this kind of. So this is our x0. So no matter where we are in our trajectory here, we can say, like, the model will always predict, or we always know where x0 is going to be according to this formula here. So you can kind of see how you can invert, or you can kind of see where this forward and backward process comes from, given this x0. Basically, xt, this formula here, which is your forward formula for DDPM, allows you to find either x0 or epsilon from any point in this trajectory here. Well, at least the approximation for it. So if we let epsilon theta be the prediction from the model, from the diffusion model, then we can just plug that in and we get something like x0 hat is equal to xt, so our current step, minus the square root of 1 minus alpha t times epsilon theta over the square root of alpha t. And this is the predict x0 from the model. So given any point here our prediction is given by this formula for x0. Is this going to be a perfect prediction? No. And that's why we need to step. This is why we just step slightly in this direction. So let's see how we're going to step. So to step, we're basically going to say the x at the previous time step. So we want to go backwards. X at the previous time step is going to be equal to the square root of alpha t minus 1, x0 plus the square root of 1 minus alpha t minus 1 times epsilon, where epsilon is sampled from a Gaussian. So this is just our formula up here, just with changed time steps here. Now what we can do is we can turn this into the DDIM formula, if you've seen the DDIM paper, by just substituting this equation here into x0 here. So we have alpha t minus 1 multiplied by x at time t minus the square root of 1 minus alpha t over the square root of alpha t, epsilon theta should be up there. So this is just x0 right here, plus the square root of 1 minus alpha t minus 1, epsilon theta, or just epsilon, depending on what you want to use. So this right here is our DDIM formula for the backward process. We can also get the DDPM formula if we expand this out a little bit more. So if I bring this outside, we will almost be there. So this will be the square root of alpha t minus 1 over alpha t times xt, 1 minus alpha t over the square root, oops, I skipped a step, of 1 minus alpha t epsilon theta plus the square root of 1 minus alpha t minus 1 epsilon theta. Wow, my handwriting is really bad, sorry. And if we take this one step further, we can get the DDPM formula. So this will be alpha t minus 1 over alpha t multiplied by x at time t minus, so this is just changing the square root over here. This will be 1 minus alpha t over the square root of 1 minus alpha t epsilon theta plus the square root of 1 minus alpha t minus 1 epsilon theta. And this is just DDPM right here. This is the DDPM formula, essentially, where in DDPM, the alphas are actually alpha bars. All right, so let's talk about these formulas here. So for DDIM, like these are the same formulas. It's just how you use them, essentially. So let me write this in red, actually. So DDIM. DDIM is essentially normal Euler. So we have x0 here, and we have x at time t is equal to epsilon. So let's say we have this noise here. And what we want to do is we want to go backwards. We want to generate an image from this noise. So assuming we have an already trained diffusion model, throughout this video, I'm going to assume we have an already trained diffusion model. We basically want to generate an image from that diffusion model. So what we do is we sample our noise from a Gaussian distribution, 0, 1, and we are going to slightly step in the direction of x0. So we use this formula here to do that. Now, intuitively, what this formula is saying is at any time t, we can basically move a little bit in the direction of x0 because we can predict the direction of x0 using this formula, as shown up here. And we can move slightly back to the noise. So I'll show what that looks like. It's basically just Euler, just normal Euler. So basically what we're going to do is we're going to move to x0, we're going to move back towards e a little bit, and there's no variance in this process. So what that looks like is kind of two interpretations of this. So let's say we're here. Let's say the prediction of x0 is right here. What we do is we move all the way to x0. So that would be this part of the formula here. And then we add noise back. So we add the predicted noise back, but with a little bit less variance. So you don't step all the way to exit time t. You only step a little bit. And then you keep doing that. You're like, oh, the prediction is here now. So you move all the way there, then you move back, and you keep on doing that. A slightly more intuitive approach is you just step along this trajectory like normal Euler, and you get a trajectory that looks like this. So this is just normal Euler. Now, if we have DDPM, this is essentially ancestral Euler. So it's a little bit different. And DDPM basically makes this variance here not variance parameterized by the model, but rather this is variance sampled from a Gaussian distribution. DDIM removes the Gaussian distribution variance, DDPM keeps it, so your backward process is going to be slightly noisy. So what we're going to do, so this is x0 and this is exit time t, which is equal to epsilon, so same starting idea. Basically, we're going to move to the predicted x0 and then move back. And what this looks like is kind of Euler over here, DDIM, but whenever we take a step, there's actually kind of some variance we're going to have. So whenever we take a step, it's not going to be exactly here. The step can kind of be anywhere in this Gaussian, and actually it could be all the way over here if we really got unlucky, I suppose. It's not going to be, but it could. So essentially, whenever you're stepping, you have variance, and the variance is going to be decreasing. So you take a step, we take another step, but here the variance decreases, and then we take another step, variance decreases more, and then another step and the variance decreases until we get zero variance and we're just left with the mean. So as we're stepping, we have this variance, which basically means you can get a noisy trajectory like this. So we could step there, and then maybe there, and maybe there, maybe there, and then to x0. So you have variance whenever you're stepping along DDPM. Now, the reason I bring this up is because these are the two approaches we're going to be using for editing. Now, this one is intuitive, a lot more intuitive than this one for how we can edit and do an inversion. DDIM, it looks like you can just, I can just go all the way back here by just following a backwards or a forward trajectory. While DDPM, we're like, it's noisy. So if we go backward, it'll probably give us a different image every time. While DDIM is deterministic. If you go backward, it'll give you the same image every time. But we're going to be inverting both of these. So let's invert DDIM. So this was, I don't know when this was first brought up or when this was first introduced. The paper that, I forget what paper it was, but I'm going to be looking at the Null Inversion paper, which brings up DDIM. It doesn't introduce it though, or DDIM Inversion. It doesn't introduce it though. But that's the paper I'm going to be kind of talking about. So what's our goal? Our goal is given an image, x0. We want to invert this. We want to invert x0 such that, invert x0 to exit time t, such that the the backward process gives us x0. So basically, we want to find an xt, so some noise, that corresponds to x0 along the DDIM process. So along this deterministic process here. Now, let me just write out the formula again. So I'm going to be changing the formula slightly. It's equivalent to the formula derived above. You can derive it. It's equivalent though. But basically, we have exit time t minus 1 is equal to, so we have the square root of alpha t minus 1 over alpha t times exit time t plus. So this is our signal here. And basically, the reason we're writing it out like this is to group our signal and our noise. If we look up here, the signal and the noise are in a term together, and the noise is not grouped together. So it's annoying to deal with. It's a lot less intuitive as well. So we're going to be grouping them in this equation here. So 1 over alpha t minus 1 minus 1 minus 1 over alpha t minus 1 multiplied by epsilon theta, our model, at time t. So, and let me write out the second formula. So basically what we want to do is we want to invert this. Now to invert this, all we're going to do is we're going to change the alpha t minus 1s to alpha t plus 1s. So this gives us xt plus 1, and instead of writing it out, I'm just going to copy and paste. I've written out enough equations. So this alpha t here will just be changed to alpha t plus 1. This will be alpha t plus 1 instead of alpha t minus 1. And this is our this is our inversion equation. So this brings us from noise to signal. This brings us from signal to noise. So this right here is x0 to xt, which equals epsilon. And this right here is xt, which equals epsilon to x0. So this is our process here. And epsilon, notice how there is no noise here. Epsilon only comes from our model. So this is a deterministic process because our model is deterministic. It's not noisy in any way. It's a deterministic unit model. So let's break this down a little bit. Basically, our alphas, so alpha t minus 1 is going to be greater than alpha t. And this is important because of the terms kind of in front of the signal and the noise terms. If we look at this first term here, we have alpha t minus 1 over alpha t. Basically, this is going to be an increase in signal here. So whenever you take a step backward, it's going to be an increase in signal. And this term here is basically going to decrease the noise. So this is a prediction of the noise by the model. And we're basically going to increase the signal and decrease the noise. That's basically what we're doing in this equation. Here, we're going to be decreasing the signal. Because the denominator is plus 1, not minus 1. It is greater than this one here. It's greater than the denominator, so it's going to be a decrease in signal, and this is going to be an increase in noise. So this is kind of the idea here. Instead of increasing signal and decreasing noise, we're going to be decreasing signal and increasing noise along our trajectory. And basically, we're going to be using this to say maybe 50 steps. We're going to be taking 50 steps in the reverse trajectory, and then we can and that'll give us a noise lane that corresponds to our image, and we can regenerate that image by using this formula up here, the normal formula, and that noise lane we produce. So what does this look like? If we have x0 here, and we have xt, which equals epsilon here, this will be epsilon theta. It's not going to be noise we sample, it's going to be the noise the model predicts. And we have our trajectory here. Basically, at any time step, x at time t, the model is going to predict some noise. So maybe this is the model's prediction of the noise right here, corresponding to that latent, I'll call this epsilon. This is epsilon theta, this is epsilon theta at time big T, is epsilon theta at time little t. So basically, at time little t, the model is going to predict the noise at this time step. Now, what the backward process does is it says, okay, we're going to step away from the noise it predicts. And this will give you xt minus 1. Instead, we're going to be going the opposite direction. So this will be xt plus 1, increasing the noise it predicts instead of decreasing that noise. So this is pretty intuitive. It's just reversing the process by literally just flipping the t minus 1s with t plus 1s. And like I said, this is deterministic. So whenever you generate there's a one-to-one relationship between an image you have and a latent that corresponds to that image, or a noise latent that corresponds to this image. So that's nice. So how do you make an edit? So we now have this process where we can invert DDIM, and we can go forward with it. So we now have this process where we get this latent. Who cares? How do we edit it? So a naive way to edit this is to take an image. So this will be an image of my cat. And what we're going to do is we're going to invert it using, say, 50 time steps. So it's just a normal diffusion process, except we use the inversion equation, and you use increasing t's. So this will be our inversion process here. And you give it a prompt. So you invert it with a prompt, say a cat. And this will be x0, and this will be x at time t. So these will be, and this will be the image. So these will be the latents, the noise latents, that correspond to this picture here. And like I said, it's a one-to-one correspondence, so there are no other noise latents that correspond to this cat because it's a one-to-one correspondence. So what we can do is we can regenerate this image by just saying, all right, I'm going to go forward with the same prompt. So we go forward by using this equation up here, the normal DDIM equation. And what this will generate is literally the exact same picture. So I'm going to copy and paste it. Right there. So this will give us the exact same picture. And this will be x0 bar. Well, almost the exact same picture. There's a little error to this process. There's a little bit of error, but we'll get to that in a second. Yeah, but this will give us a very, very similar image, almost exact. Now, if we want to edit this image, what we can do is we can basically, we have these latents corresponding to an inversion with the text a cat. Now, instead of going forward with, this will be forward. Instead of going forward with the text conditioning a cat, we can go forward with a cat in a hat. And this will hopefully generate a picture of our cat in some hat. Of course, it'll be a little bit different from the cat, but it'll hopefully be very similar to the original picture we had. And it'll hopefully be much better than other editing processes because we start off with the current picture of the cat. So this is the inversion technique. And since this is continuous, this is a continuous mapping, slightly perturbing this should slightly perturb the output, and it should be very similar to your input image, and it usually is very similar to your input image. Now, let's talk about the downsides. So this process kind of feels a bit weird up here. It should, because we literally just switched out alpha t with alpha t plus 1, and it is a bit weird. And it results in problems. So if we have CFG equal to 1, this is fine. I guess it's okay, this process works. But the problem is if you want to edit any image, you need a CFG greater than 1. And that's just because a CFG equal to 1 basically, like, it results in a very similar image. Like, it doesn't do very much. It doesn't allow you, CFG basically changes the image according to your prompt more. But if you have a CFG equal to 1, basically if I change a cat to a cat in a hat, it's not going to do anything because our CFG is so low. Now, if we have a CFG greater than 1, basically whenever we're inverting, we're going to get some latent. Then that's fine, but it's going to be off. The trajectory here is going to be off. And that's because this trajectory accumulates error, and with the CFG greater than 1, it accumulates more error. It's on a different trajectory than the trajectory that generated the original image. So it accumulates error. Now to fix that, we use something called Null Inversion, or at least that's one way to fix it. And yeah, so that's one way to fix it, and I'll talk about that. I think there are other ways, but this way is pretty good. The problem is it just requires training, but I think it's a pretty good way. So let me go over null inversion. Basically, the problem is we have this trajectory generated by DDIM. So we have x0, we have xt, and let's say our normal trajectory is this here. Actually, I'm going to draw it out a little bit bigger. So basically, we have our picture of a cat. Say here. That picture just keeps getting worse and worse. And we basically invert it with CFG greater than 1. So what this will do is it'll generate some trajectory here. Let me move this a little bit back. Say over here. That's better. Yeah, that should be enough points. So what we're going to do is we're going to take x0, we're going to invert it using the process described above. So this will generate some trajectory like this one here, where this is x at time t, which is equal to epsilon, and this is x0. So this is just what I described above. But the inversion is going to be done with a CFG greater than 0. Now, if we take the inverted image here, so whatever this noise lane is here, and we use the process described above, what we're going to result in is some terrible looking image. It's not going to be good. So whenever we invert it, it's going to accumulate more and more error, diverging from the original trajectory more and more. So we keep doing this more and more, and we get some image. Maybe this will be like x0 hat. This is the predicted image, and maybe it looks something like, I don't know, like that. There we go. There's our new picture of a cat. Yeah, this isn't very close to the original picture of the cat. It still has cat-like features though. But basically our reconstruction here, this is our reconstruction with the CFG greater than 0, results in a lot of error accumulated during this trajectory. Now, we know what the trajectory was to get here. What we can do is we can say, well, if we follow this trajectory backward, we'll get the original image, obviously, if we follow this trajectory backward, because this is a deterministic one-to-one correspondence. But the problem is the trajectory we have is slightly off, and that's because the diffusion model is making predictions kind of in the direction towards this rather than the direction over here, because the CFG is greater than 1, not 0. So intuitively, all we need to do is we need to take the trajectory that was the error trajectory, and we need to make it the original trajectory, though we want that with the CFG greater than 1 because we want to edit this image with text. So what we do is we just say, well, if we start from the end of the trajectory, because it has the least amount of error, we can take the points here, the predicted points. So if we look at this point here, maybe this is x at time big T minus 1, and this is the predicted x at time big T minus 1. What we can do is we can take this prediction and we can move it closer to the original one. And this is the idea behind null inversion. What we're going to do is we're going to take our image, we're going to invert it with the CFG greater than 1 so we can edit it, and then we're going to take the reconstructed trajectory and we're going to move it towards the original trajectory. And if we have such a trajectory, we can make edits along that. And it's basically the process up here, just with the CFG greater than 1. So let's see how to do that. So if we take a look at a unit, at a fusion model, we basically have an image here. So this is going to be our image x at time t. And we have our unit here. Unit. Now, if we condition this on two things, say, or if we're doing a CFG, we're basically going to condition this on some text. A picture of a cat. So these will be our transformer embeddings that we're going to condition the unit on here. So we're always going to be giving it the same image. And what this will do is this will give us a conditioned output, x at time t, given the condition c, where c is the text, a picture of a cat. And we also send in a null embedding. So this will be some embedding, and if we're using clip, this will be some embedding that's 77 by d, and this will also be some embedding that's 77 by d. Or if you use some other weird null embedding, I'm going to be assuming it's just like nothing, it's just no text. So you can send this through, and this will give you a second prediction, epsilon theta, xt given the null embedding here. And you combine these together to get your prediction, epsilon theta CFG, or something like that. And this is your noise prediction, rather than either of these individually. So what the authors of null text inversion do is they say, if this is our prediction, and this prediction is basically gives us this bad trajectory here, and we want to minimize the error between these, there needs to be some way to minimize the error between predictions. I wrote down epsilon theta up here, but like I mentioned above, you can get xt and epsilon theta, you can get equivalently. So you can get the predicted xt from the predicted epsilon theta. So they're equivalent. But basically, we want to minimize the error between the real part of the trajectory and the predicted part that has error. So this is a minimization process. Now, how do we minimize things? Good old backpropagation. However, there needs to be something we need to update. So the idea is we have this null text embedding here that is basically useless. Like, it's just there to do this conditioning. What if we freeze this entire process here? So I'm gonna draw that in blue. So for every prediction here, we have this entire process here to get this CFG output. And for the CFG output, we have a condition output and a null output. Now, if we freeze everything but the null text input, what we can do is we can optimize this null text input such that the CFG output will result in the correct prediction here. So we're taking the bad prediction and we're going to optimize it such that it leads us to the right prediction. And we're going to do that step by step. So starting at the end of our trajectory, we're going to minimize the error here. So let's say we minimize the error and it gives us, like, we minimized it perfectly. Then the diffusion model is still going to predict a bad prediction for the next step. So it'll give us something like this. So then we minimize this error here, and then it gives us another bad prediction for the next step. And we do this for all steps until we get this perfect trajectory. And we're going to save each of these new null outputs corresponding to each of these. So it's basically an optimization process going from the end of the trajectory to the beginning of the trajectory. And the way we do that is by minimizing the mean squared error between the prediction at time t. So like I said, prediction epsilon theta and xt are equivalent. So I'm just going to be writing xt here. And epsilon theta, or I guess this can just be like the row epsilon, but whatever. I'm going to be writing xt. You get the idea. So epsilon theta CFG. And epsilon theta CFG is composed of epsilon theta of xt given the condition. So that's this part up here. And it's composed of epsilon theta of xt given the null embedding here. So what we do is we just do backpropagation, where the thing we're training is going to be the null embedding here. So we just update the null embedding such that the trajectory, such that the error between the trajectories is minimized. So once we do this, and you can do this quickly, relatively quickly, it still requires compute, but you can do it relatively quickly. Once you do this, you will have a perfect trajectory with the CFG equal to whatever CFG you were using. Now that means you can edit the image because you have a CFG greater than what you had before. So you can use the process described up here to edit your image. Now that you have this trajectory, just instead of using a null embedding for each part of the trajectory here, you're going to be using the trained in quotes, null embedding from the process described here. And this is null text inversion. They have a picture here, but yeah, this is the idea behind null text inversion. So this is a cool idea. I like this idea, but the problem, there's a lot of problems with DDIM inversion, and that's you invert it with the CFG greater than 1, and it incurs this error, and this error you have to train this thing, and it still requires training, which is expensive compute-wise, and it's expensive time-wise. Now, you can do some good edits with it. They show down here some interesting edits they do. Where's the donut? Here we go. So some interesting edits you can do with this. But like I said, it still requires training. Like, these are some pretty good edits. Even cherry-picked. They're probably cherry-picked. But notice how it just changes kind of the thing you want it to change. So, or kind of the change you make in the text. It does a pretty good job with that. If this is kind of the input image here, it does a pretty good job with editing what you describe. So red hair, it changes the hair. And it barely changes the rest of the image if we look here. Like, this is the input image, this is the output image. There's some parts it changes, like the mouth, but it does a lot better than most techniques. Like, you can see the background and everything stays the same. So this is kind of the first thing I wanted to show. Null Inversion and DDIM Inversion. I think it shows some promise for image editing. And there's probably a way to invert it that may be better than DDIM. And now let's talk about DDPM. So DDIM and Null Inversion does pretty good, but it requires training. And also notice how this is a deterministic process here. So that means that this edit here is always going to be the same edit, because this is deterministic here. I mentioned above that variance is bad, but variance can be good if you have if you add it in a nice way. So variance can be good in some cases. Here, in a lot of cases, it's not that good if you want to make a deterministic edit, but it's nice in this case. It would be nice to have some variance such that a red-haired man kind of changes a little bit. Maybe you want a different style of a red-haired man. So that's where DDPM inversion comes into play. Let's talk about that. You go to DDPM inversion. An edit-friendly DDPM noise inversion, noise space inversion and manipulations. So this is DDPM inversion, and it is very similar to DDIM inversion. The idea is the same. But the nice thing is you don't need a null inversion, and that means that it's really, really fast. All you need to do is go backward, and you're fine. And then you got this nice thing you can edit. And there's a reason the CFG error doesn't get accumulated, and I'll show why in a second. So basically, the problem with DDIM is it's a one-to-one correspondence, so it can't edit very well, but it also requires training, which is very slow, because you need this null inversion, for now at least. So let's use DDPM. Now the problem with DDPM is it has this noisy trajectory, like I showed up here. And if you invert it to this here, it's not a one-to-one correspondence here. There's variance around this point here. And since there's variance, that means any of these points here are just as good of an inversion for x0 here, but that doesn't mean it's going to be x0 either, because there's variance. So whenever you invert it, you're going to get some point that kind of corresponds to x0, because like it's in the domain of the diffusion model for x0, but it won't necessarily generate x0. It may go around in some place, and it may generate something close to x0, but because there's noise, it's not going to be an exact recreation. And it may be something completely different because there's a lot of variance in this backward process. Unlike DDIM, where it was a one-to-one relationship. So how the heck do we generate a trajectory where we get this one-to-one relationship? So the idea they have here is to basically invert this and to kind of save the noise. So let me go over how they do that. First, I'm just going to write out the steps. So basically the first step is to go forward. So this is going to be adding noise to your image. So say we have an image. What we're going to do is we're going to do the forward process to get xt corresponding to x0. So now we have xt and axt that corresponds to x0. It's not the xt, it's not the noise lane that corresponds to x0, it is axt that corresponds to x0. So this is just a normal forward process, like if you were training a diffusion model, just normal forward. So now what we do is we go backward using this noise latent here. And what we're going to do is we're going to use our diffusion model, and we're going to store the added noise at each step. So we're going to store the noise at each step. So remember our formula, xt is equal to the square root of alpha t, x0 plus the square root of 1 minus alpha t, epsilon. And in this case, epsilon is sampled from Gaussian. I'm not going to write 1, or I'll write 1, and this is our variance here. So if we do this, we're going to get the problem I mentioned above, xt. So it'll generate this trajectory here, and it'll be something close to x0. Now, what we can do is we can say we can assume that this is basically a part of the image. So we can basically make the claim that since the noise is required to have this reverse, or to have this backward process, it's inherent to the image. So the noise and the image are not different. The noise is the image itself. It is a part of the process. Why wouldn't it be a part of the image in DDPM? So what we can do is we can say, like with DDIM, we have this trajectory here. And this trajectory here, basically at each time step, you have a x at time t that corresponds to that. What we can do is we can invert this, and we can say, well, there's an x at time t, but there's also an epsilon at time t that corresponds to x0. So whenever we're inverting this, we can say that there's an epsilon t, my bad. And the epsilon t corresponds to that time step. So epsilon x at time t big T minus 1. And this will also have an epsilon at big T minus 1. And if we force the model to generate x0 by basically doing this interpolation here, where you slowly reduce the variance, you can get x0 and you can get the epsilons at every time step here. So what this will do, let me scroll down here to give the formula here. Basically what we're going to do is we're going to go forward, we're going to generate xt, and we're going to go backward, accumulating the epsilons at every step. Since the xt is deterministic, the prediction for the noise here, the model prediction for the noise is deterministic. We don't need to collect those. That's going to be what's going to be used for the edit, while the epsilon theta, or while the epsilon t's, the sampled noise, is not deterministic. So we're going to be accumulating those. And basically this will give us a noisy trajectory going backward. So what we're going to do is we're going to store x at time t. So this will be our noise corresponding to x0. And we're going to store a trajectory that regenerates x0 by just doing a backward process and forcing the model to generate x0. So we're going to have, they call it zt over here, but I called it epsilon t. So epsilon 1, or epsilon big T to epsilon 1. So that's what we have here. Basically, this right here is the forward process. So this goes from time step 1 to time step t. And this goes from time step t to time step 1. So this is a reversal process. And basically, we're going to be collecting these ZTs here, which are going to be basically the predictions. And this will basically be the noise that we're going to add. So if we look here, we have x at time t minus 1. So that'll be one step in the past is equal to the mean. So this is the predicted mean plus some variance here. And we're going to be storing these ZTs here, where the ZTs correspond to the noise. So that's just this right here. So we're going to be storing these along the backward trajectory. And that means we can recreate a trajectory going to x0, and that's fine. The reason you do it in this way is because if we have the model predicting the mean, and we have, and this is deterministic because the model is predicting it, then we can invert this process, but we can change this here while keeping the noise static to allow the model to make an edit to the trajectory. But the nice thing is we can form multiple trajectories if we change ZT here, multiple trajectories going to x0. So this gives us the variance I was talking about earlier. We still have a deterministic way to get to x0 if we form a trajectory and we store all the intermediate steps. But if we allow the model to edit that trajectory after we store the trajectory, then it edits x0. Let me write this out more formally. So basically, reiterating, step 1 is to go forward. So go from x0, our image, to x at time step t, finding a noise latent that corresponds to x0. Then what we do is we invert this process, storing, and we invert it using a noisy process. But since we have a formula where we slowly decrease the variance, we can end at x0. So this is just a normal backward process. This is a normal backward process like you were generating an image, except we force it to generate x0. So this is, and we can accumulate the error here. Basically, this is the error between the predicted x at time t and the actual x at time t. So this essentially forces it to go back to x0. But basically, we can store the noise at every time step here, creating a noisy trajectory that is deterministic. So it's a noisy trajectory that does lead us back to x0. So now that we got this, we have the noise at every time step, allowing us to get back to where we want to go. And the starting point for that trajectory, we can do what we did up here, all the way up here, where we do the inversion, we collect the trajectory, and we do the backward process. That should be backward. We do the backward process with a different caption. So they don't have it over here, but basically now that we have this trajectory here, we can say, okay, model, at every time step, instead of saying the predicted, so x at time t, is going to be equal to, say, this up here. Basically, we're going to invert this trajectory and we're going to have the model make predictions. So step 3 is going to be re-invert the trajectory. So go backward again. And instead of going backward with this formula up here, we're going to take this formula. So this is our formula for going backward. Or rather, the formula was up above here. Let me just copy that formula. So DDPM formula right here. Let me take this. So this is our formula for going backward. Right here. There we go. So if this is our formula here, we're going to take this formula and we're going to basically keep this part static here by taking the epsilons that were produced from the first backward trajectory and storing them here. And this means if our model predicts the exact same thing, we're going to get x0 again. However, since our model is conditioned on some caption, we can change the caption so that the trajectory is changed slightly here. And this allows us to make an edit to our image. So this is the idea. Go forward, go backward once, collect some noise, go backward again using that noise and changing the signal. So go backward once, collect some noise, go backward again, change the signal. And this allows you to make an edit to the image. And this doesn't require any null inversion. It doesn't require, and you can also change the CFG. And the reason you can change the CFG is because you have this error collection term here. So I mentioned that you're collecting noise here, but the trajectory that you're making isn't going to be perfect. And that's because the model, basically you want the model to predict all the noise that was added. You basically are adding noise, and you're like, okay, model, what noise did I add? Obviously, that's how you do it. That's how you trained the model. But the model isn't going to make a perfect prediction. And what you can do is you can treat the error the model made and just store that in the noise. We're already storing noise going backward. Why not just store the model error as well? So you store whatever error the model made, giving you a prediction off x0, and just store that in the error so that the model makes a prediction such that you get back to x0. So that's all you do. And basically this allows you to have any CFG scale you want. And since you're just throwing the error in the error term that we're collecting along the backward trajectory, it doesn't matter. You still get this perfect reconstruction. And this allows you to make nice edits with a high CFG scale. So this is DDPM inversion. Now, I want to talk about how do you make a good edit. The approach I mentioned, where you just invert it, and then you make an edit on the backward process, is good, but it can be made better. And now we're going to talk about prompt to prompt. So this will be the last thing I talk about. This video is already long enough. I told you it was going to be long. Prompt to prompt is a way of editing images, assuming you have a trajectory. So it assumes you can create a trajectory like this. Now, this isn't a problem if you're generating an image, but what if I want to make an image, or what if I want to make an edit to an image that is already generated? This is why you need inversions. Inversions allow you to collect a trajectory going, basically allow you to get a trajectory going forward. And since you can get a trajectory that is deterministic, you can make edits to that trajectory. And since it can recreate the original image, all you have to do is make small perturbations to that trajectory, which should give you a nice edit. And prompt to prompt does that. It assumes you have a trajectory going backward, and you use that trajectory to make an edit. So let's talk about prompt to prompt. It's pretty simple. Basically, it messes with the cross attentions. So if we know diffusion models have a cross attention mechanism, and the cross attention is so we can edit using text. So let's look at the cross attention. So we have our cross attention, and our cross attention looks like this. So we have our output. So output of the cross attention is equal to the softmax of our queries times the keys transpose over the square root of the dimension multiplied by the values. Yes, I know everyone knows the good old attention formula. Basically, if we break this down, the keys and the values, so the keys and values, this comes from our text. And the queries come from the image. Now, let's interpret this. So if we look at this here, this first part here, the softmax part, basically says, how will the tokens be combined? And the value part is saying what tokens will be combined. So these are just our tokens here. This is saying how will we combine these tokens here. And remember, this is the text, and this is basically a relationship between the text and the image. So under this interpretation, let's draw out a picture. So let's say we have like 4 tokens or something like that. So I'm going to split this into 4. This will be our attention mechanism. We'll call that like, they call it M in the paper, so I'll call it M. That's this part here. And then we have our tokens. So we have 4 tokens here corresponding to 4 text tokens. So let's go ahead and interpret this. Basically, these are our queries, and these are our keys, and these are our values. So if we, and this is our image, this corresponds to the image, and this corresponds to the text, and this corresponds to the text here. Every token corresponds to a text token. This corresponds to image and text relationships. I'm going to be using this image in a second, but it's a good way to interpret it. Basically, every column here, which corresponds to the text, basically says, so for every column, it basically says where in the image is said token. So if this token here corresponds to, I don't know, bear in this case, this basically it has some relationship with the image. And the relationship with the image basically shows, it'll hopefully, if it does what it's supposed to, it'll have a high correlation with a bear and a low correlation with everything else. So it'll give you an attention map like this. So intuitively, this is what you may see if you try to interpret the attention maps here. You'll see there's high correlation between bear and the picture of a bear, and for the bird as well, and a picture of the bird. So basically this says where in the image is a text token. Now let's stick with a simple idea. Let's say we have a, let's just do a simple edit. So let's say we have a picture of a cat, and we want to change this to a, I'll do a happy cat, actually. And let's say we want to change this to a picture of a mad cat. So we just want to change out one word. Basically, the idea is we have our picture here. And let's draw a happy cat. There we go. Good old happy cat. If we look at the attention part here, the attention part here is the relationship between the text tokens and the image. So if we look at the column for happy, that should hopefully give us some region right here with high correlation, and it should give us low correlation elsewhere. While the rest of the words here don't matter for the edit we're trying to make. So the idea is we want to keep the structure the same, but we want to change one word. So what they do is they keep the structure the same by saying we're going to keep the attention map the same. So we're going to keep the area, the area that has high correlation between happy and the image. We're going to keep that the same. But what we're going to do is we're going to change out the token. Maybe this token here corresponds to happy. And we're going to change that out with the text token for mad. And what this will do is it'll only edit the region with high correlation on the attention maps. So what this will, let me take the image here. And this should make an edit that'll hopefully look something like that. There we go. And it should only mess with that region. So maybe it was a little, I don't know, it's a little messy over there with some added noise, but it should only edit that area where the attention is attending to, rather than if you didn't do this, this word mad could attend to something else. Maybe if I change that from happy to, I don't know, sad, it also changes the background and there's like storm clouds and stuff. But if I only wanted to change the emotion of the cat, which is what it was before, then this works really well. And basically all you're doing is you're keeping the structure of the image the same, and you're changing out the token that corresponds to that. So keeping the structure, changing the style, that's the intuition behind prompt to prompt. Now they have an image over here. Let me just take a look at that. Basically, it's what I showed before. You can swap out words by just changing the words with new words. Yeah, they also have this part here, adding a new phrase. Basically, for adding a new phrase, I think all you do is you keep everything static that didn't change. So if I wanted to add a picture of a happy cat in the city, maybe then I would keep a picture of a happy cat. I would keep those attention maps the same, and then I would just allow it to add new attention maps. And then attention reweighing, you can weigh attention maps higher. So if you weigh an attention, if you weigh like some attention map higher, then intuitively it'll weigh that token higher. So you can weigh stuff higher than you can weigh tokens higher than other tokens, and that allows you to make a better edit for a certain word. The way you do this is you do a forward pass. Let me go down to the algorithm. You basically do a forward pass with the original prompt, and you store the attention maps, and you do another forward pass, and you basically just send the attention maps through. You basically just replace them. So you edit the attention maps in some way, and you do another forward pass, but you replace the attention maps with the edited attention maps. So basically just replacing like keeping these the same. And if there was in a city, you would not change that attention map. So this is prompt to prompt, a good way to change your image in a nice way, assuming you have a trajectory. And both these go hand in hand very nicely. The inversion approaches and DDPM. This allows you to do a nice edit to an image you already have. Now, this is all I really wanted to talk about. I know it was a lot, but basically I want to re-mention a reason why I think these are why inversion is cool, and I think it'll be a good way to make edits. The first is this is deterministic. It allows you to make an edit, or it's deterministic and allows you to make an edit that doesn't veer far from your original image. It's not noisy, unlike the other methods that we have. And the noise we do add through DDPM is still a deterministic recreation. It's just noisy so that you can change the edits you make. But the edits are still going to hold true to the original image you had, unlike many other methods. The second thing is you can prompt to prompt, and you can prompt to prompt with different modalities. Let's say I instead have cross attention with an image, and let's say I'm generating a video. I can do an inversion on an image, change to the image, go forward, do the backward process with a different image, and that is very similar to this, but instead of changing a word, I can change the image. So you don't just need text. You can't just make text edits. You can make image edits. And remember, this doesn't require any training, unless you're doing null inversion, but I wouldn't really call it training. This doesn't require training. This is a powerful edit technique with no training at all. And the third thing is inversion and edits are usually pretty fast. So like DDPM inversion is pretty fast, and it only requires you to invert once. So yeah, I think this is a cool approach that I've been seeing recently, and I just wanted to kind of share it. Yeah, let me know what you think about it. I'm curious to see if this becomes a good approach. I think it's cool because it's deterministic and it makes nice edits. But I don't know. We'll see if this becomes if inversion becomes a cool a thing that's used commonly, like image to image and in painting.